So now let's put everything back together. So we're going to talk about our reaction. We're going to talk about carbocations and how the big picture looks. All right, so we're going to take 2-butene. So let me just draw that picture. So you have it down here. And so if we draw this, 2-butene would have a double bond, right, in between the two carbons. And then we're going to have HBr. And we want to see how these two react. Okay. So we're going to take our double bond, and it's going to reach out and grab that hydrogen. Right? So it's going to grab a hydrogen. And in that process, right, we're going to grab the hydrogen, and that's going to be our transition state. And we're going to get to this intermediate. Right, that's going to make a carbocation. So if you notice, and let me highlight this in orange, there was one hydrogen here. Now there's two. So we've lost the double bond. Right? We lost it and added a carbocation here. So this is our intermediate. Now we're going to take that carbocation, and the bromine is going to add in. Right? And so as that bromine is adding in, that's the transition state. And when it finally makes the product, it stops down here at the bottom. All right? So we form this intermediate. So we have two activation energies, right? A big one and a little one. Whichever is the biggest is the rate determining step. Right? So getting that first group to go is the rate determining step. Adding that second one in is easy because that carbocation is so reactive. And then lastly, the products are lower than when we started. So even though it took a good amount of energy to get the reaction started, at the end, our reaction is exothermic, right? We're going to give off energy. All right, so we've just talked about, and let's do one just to kind of see it from start to finish. We just talked about if we have a double bond, and we add HBr, we could add one hydrogen, one bromine. All right, so go ahead and pause the video, give this a try, and then we'll do it together, and that'll lead us into this next topic. All right, so hopefully this went well for us. So one thing we should always think about is our attention should go right to the two carbons that are part of the double bond. One of them is going to get the hydrogen, one of them is going to get the bromine. The hydrogen is going to add to the carbon that has the most hydrogens already. So let's draw that out. This one has two hydrogens. The inside one has one. So that means that green hydrogen is going to add to the outside. So we'll draw our molecule. Remember, we always lose the double bond. And so I'm going to color code the hydrogen. So I'll leave them. The ones that were already there are going to be in blue. And then the true groups we're going to add were in green. So I'll keep them in green. We add one hydrogen to the outside. And we add our bromine to the inside. All right, so that non-hydrogen always goes to that more substituted carbon, right? The carbon that's attached to more carbons. All right, so if you remember, that's called Markovnikov's rule, right? Adding to that more substituted, right? The hydrogen is going to add to the carbon that has the most hydrogens. The non-hydrogen adds to the more substituted carbon. All right, so the next reaction we're going to do is hydration. And it's just adding water across the bond, right? When we talk about someone being hydrated, it means we're adding water. Dehydrated means losing water. All right, so this reaction is going to be acid catalyzed. Right, and so I'm just going to color code these. So my acid catalyst is going to be this H2SO4. All right, so that H2SO4 is just going to be my catalyst. Remember, if you think back to Gen Chem or your previous chemistry classes, a catalyst doesn't show up in the reaction, right? And it doesn't get used up. So it won't be my limiting reagent, and it won't show up in the product. So we're not going to see SO4 in our product. It's just there to kickstart the reaction, right? So those are just both good acids. All right, so it's just our acid. All right, the second part is it's regioselective, and it's going to follow Markovnikov's rule. All right, so what we're going to see is a hydrogen is going to get added to one of these carbons, and OH is going to get added to another. All right, so on one of the groups, you're going to get an OH as our alcohol. On the other one, we get our hydrogen. All right, so based on the example up here on the right, pause the video and show me what you get for these two, and then we can talk about it. All right, let's see how everybody did. So the CH3 is going to stay exactly the same. All right, the next carbon already had one hydrogen, so it'll stay there. And then on the other side, it's going to get the OH. And then it turns into a CH3. Okay? So this hydrogen is the one that's already here. This had two hydrogens to begin with, and now it picked up a third, right? Because we had a hydrogen and an oxygen. Same thing on the bottom, CH3, carbon, CH3. So those two CH3s I've drawn were the ones here on the top and left. We didn't do anything to them, so we left them the same. And then off the center is where we get our OH. And now this turns into a CH3. So it picked up one of the hydrogens from water. And that's why it became a CH3 from a CH2. And we add the OH to the more substitute. Right? So Markov-Nikol's rule tells us the hydrogen adds to the carbon that already has the most hydrogens, and the OH adds to that other carbon, the more substituted. All right, let's try one more. So we're going to put our water and H2SO4. All right, so again, pause the video and give it a try and show me what you'd get. Let's see how everyone did. So our carbon framework is going to stay the same. So that's kind of where I would start, is just redraw the carbon framework exactly how it is. And then we can put all the groups. The OH is going to come off the more substituted, right? It's off this carbon here. And then my hydrogen gets added to the other side. Now, one new nuance that we can do is, remember, this is our zigzag form. So we actually don't have to show the hydrogen. So if you want to write it to explicitly show that it's there, that's fine. But actually, in the zigzag form, you'd be fine just putting the OH, right? Because we know that hydrogen is implied. All right, so just like we did for the HBr, let's kind of walk through this. All right, so where you're going to start off with is your double bond is your nucleophile. Okay. And the reason we do this in acid, right? So we have an acid catalyst, is our water is going to pick up a proton. So the double bond is going to reach out and grab that hydrogen and push the electrons back on the oxygen. Right? So that's why the oxygen now has two lone pairs and remakes water. Remember, the hydrogen goes to the carbon that already has the most hydrogens. And we're only comparing the two that are part of the double bond. So this one has one, this one has two. So this turns into a CH3. The other one picks up the carbocation. Now, once we have our carbocation, our oxygen becomes the nucleophile. So these lone pair are going to push in, and they're going to add into that carbocation. Right? They're actually going to push in to that empty p orbital. Right? So we're going to push our electrons in, and this is where our alcohol is going to come from. Now, this OH actually has an extra hydrogen, right? You can see that with the positive charge on the oxygen. So now a water molecule picks up that hydrogen and gives its electrons back. All right, and now this water molecule can go start another reaction. And so that's why we can use the acid catalytically, because we regenerate that proton. I hope that was helpful in terms of being able to see the big picture of how the reaction goes forward. So remember, this is called our reaction mechanism. So we're actually drawing the arrows of exactly how each atom is moving and being new bond is formed or broken or atoms are transferred. Let me add one more wrinkle. All right, so this is probably the trickiest part of these reactions, is anytime we make a carbocation, so this is only when we have a carbocation, so I'd really highlight that idea, that when we talk about a carbocation, we have the possibility of rearrangement, and literally the molecule can rearrange. The reason this would happen is if we could form a more stable carbocation. All right, so if we can form a more stable carbocation, we'll get rearrangement. And so just to review, remember, if we go from primary, secondary, tertiary, and so the tertiary is going to be the most stable. All right, so for example, we'll rearrange if we're a secondary and can move to a tertiary. We won't ever go the other direction, but we'll definitely go in this direction. So primary would rearrange to a secondary or tertiary, but a tertiary won't ever rearrange the other way. All right, so that would be the driving force for this rearrangement. All right, so let's take a look at this one. So Same step as before. Our double bond is going to be the one that reaches out and grabs that hydrogen. And it's not shown here, but in our mind, we're going to know that the hydrogen has a partial positive, the chlorine has a partial negative. So our electrons reach out and grab that hydrogen, push the electrons on the chlorine. We want to look at where that carbocation is. Right? So it was on the more substituted. Right? So it's still better than being on the outside. It's going to be on the inside. And so it's a secondary carbocation. So what we're going to do, anytime you make a carbocation that's not a tertiary, you want to stop and look. If I move this carbocation one to the left or one to the right, can I move up in substitution? Meaning, can I go from a primary to a secondary? Or can I go from a secondary to a tertiary? Right now, we're already a secondary, so we would only rearrange if we can get to a tertiary. So I can see that if I move it to the carbon one to the left, it's 1, 2, and then you can count the carbon where you were at, so it's 3. So we're actually going to move it over 1. And so what we can actually do is we're going to move the hydrogen over. All right, so this is called a hydride shift. And the reason it's a hydride shift is because we're moving the hydrogen with its electrons. So the hydrogen and those 2 electrons are going to move over. And now it gives that carbon its octet, and the one before now only has 6 electrons. And so what we've done is we've taken a secondary carbocation and converted it to a tertiary. All right. And so does everyone see we moved the carbocation from this carbon here on the right to the one in the middle. And so these two switch places. The carbocation and the hydrogen switch places. And we did it because we can get to the more stable tertiary carbocation. All right. So the big thing here is if you're going to go up in substitution, then you'll rearrange. All right. So this only happens when you have carbocations. But if you have a carbocation and you can go up in substitution, meaning you're going from a secondary to a tertiary, then you'll probably rearrange. The easiest thing to shift is a hydride. So the first thing you want to look at is there a hydrogen you can move? All right, so you can move a hydride, so which is a hydrogen with its electrons. So that's why I put the stick. So you can move a hydride. If there's no hydride, then we're going to talk about that you can move a methyl. Right. If you have both, the hydride gets moved first. All right, so if you have both, you're going to move the hydride first. All right, and just think it's easier to move something small than it is something big. All right, so let's go ahead and draw the product of these two. I'll give you a hint. The group here is already highlighted that's going to shift, right? There's no hydride implied because there's 3 carbons, 1, 2, 3. And so we're going to move the methyl group over. So draw your product. Here, there is a hydrogen implied, so you'll do a hydride shift. All right, so try both of these and we'll do the product together. All right, so hopefully that went well. So I'm going to draw the intermediate. You wouldn't have to, but we could draw something like this. And so after that first step, we would have a secondary carbocation. Right, so this is a secondary. And so what we can do is move that methyl group over. And now it gets to a tertiary carbocation. At that point, your chlorine can add in. All right, and so we draw our product. Sorry, I forgot the methyl group that moved. Right, that was our methyl shift. All right, and then let me just highlight again that methyl group that moved over. All right, so that's why that methyl group moved over one, so we can get to that tertiary carbocation. Here, let me actually draw on the hydrogen we're going to move over. So it's there in red. So on step 1, you would have gotten that carbocation. And we have our hydrogen. We're going to do our hydride shift. So our hydrogen will move over 1. Now we've added our hydrogen and our carbocation becomes a tertiary. And then my water, oh, sorry about that. Now my water can add in. Okay. And I've left it, you don't have to draw in that hydrogen because it's the zigzag form. But I think sometimes early on, it's nice to highlight exactly what's moving on. So the thought behind this is if you create that secondary carbocation, you always want to pause and say, can I rearrange the molecule to get a tertiary? And if the answer is yes, then you should do it. And you're only going to rearrange a hydrogen with its electron, so hydride, or a methyl group. All right, so I think these reactions are a little different than probably what most people have seen before. So why don't we take a second and just kind of practice these? All right, so what I would do here is pause the video and work each of these reactions. One hint just for kind of the way we write stuff, H plus is the generic symbol for some acid catalyst. Okay. So a lot of times we don't actually care what the catalyst is. So if it makes it easier, you can think of it as H2SO4, right? So that would be a good acid catalyst. So a lot of times people will just write H plus, meaning we need some acid. And so in the previous reactions, we've used H2SO4. Okay. All right, so go ahead and pause the video and let's give these a try. Let's see how everyone did. So on the first one, you want to add to this carbon up on top. All right, so we're going to have our double bond. So these are going to be the two carbons we care about. If you're worried about rearrangement, this is already going to be a tertiary carbon. Does everyone see that? It goes 1, 2, 3. And so if it's a tertiary carbon, then we're done, right? We're not going to have rearrangement on a tertiary. So that makes our life simple, that there's not going to be any rearrangement. So we'll redraw the carbon chain just the way it was. We put our groups. And then remember the chlorine, let me put that in green, comes off the more substituted one. And the hydrogen gets added to the one where there was the most amount of hydrogens to begin with, right? So there had been 0 hydrogens implied here. There would have been 1 implied here. All right, on this next one, when you see water and acid, it means you're going to add an OH to one hydrogen and a hydrogen to the other. Same thing as before. We're going to add to these two carbons. This one's attached to 1, 2, 3. So that's going to get my alcohol. And again, since it's a tertiary, we probably don't have to worry about rearrangement. So let's just draw the molecule the way it is. My OH comes off the more substituted, and your hydrogen comes off that least substituted because there was more hydrogens implied, right? They're not shown, but they're implied. Okay. And again, it's zigzag. So if you don't want to show that hydrogen, you don't have to. I'm just doing it here because I feel like it helps visualize exactly what's happening. Same thing with the bottom one. We're going to add to these two carbons. Again, this is already a tertiary, 1, 2, 3. So we don't have to worry about rearrangement. So we'll add our group. Our bromine is going to add to that more substituted, and our hydrogen to that least substituted. Now, in any of these, as long as the bromine is coming off of this carbon, it doesn't matter if you drew it going up, to the right, or to the left. Same thing over here, whether it's going to the right, to the left, or down, and same thing here, to the right or up. As long as it's coming off that carbon, you're in good shape. All right, let's try a couple more. All right, so the same, I'd go ahead and pause the video, give it a try, and then we can do it together. All right, so let's see how everyone did. So when you see the double bond, your attention should go right to it. We know that we're going to add the chlorine and the hydrogen to one of these two carbons. The hydrogen is going to go on the outside because that's the one that has the most hydrogens, and the chlorine will go on the inside. And then again, we're losing the double bond. So the chlorine goes here, and we don't have to show the hydrogen. If you wanted to, you could have drawn it. There's 2 hydrogens implied and 1 here. So that's why the hydrogen went out here. And so remember, in the zigzag form, it's implied there'd be 1 2, 3 hydrogens, and then still just the one original. All right. Now, one thing I want to point out is we've been talking about the tertiaries, right? That we don't have to worry about them rearranging. This one would be a secondary carbocation in the middle. The problem is if we move one to the left and we moved one of those hydrogens over, it would still be the same thing, right? It would be a secondary. We're not going to make a lateral movement because essentially we're doing work for no gain, right? So if you're going from a secondary to a secondary, we're going to leave it alone. We only rearrange if we're going from a secondary to a tertiary, right? And so that's kind of the important thing is we're only going to rearrange if we're going to go up in substitution, right? And so if we're not going up in substitution, then we're not going to rearrange. All right, so let's give this a try. So we're going to draw our cyclopentane. We put our group. This one has a wedge, so we're just kind of showing a little stereochemistry. And now on the other side, what's going to happen is this is my more substituted carbon. Again, it's a tertiary, so that makes it a little bit easier. So we know the bromine is going to add to that spot. So let me color that in orange, right? It'll add to the more substituted. The other group, the hydrogen, is going to add to that least substituted side, right? So it's going to add to that other one. So let's put those in there. So now on the more substituted bromine, it's going to go on that more substituted carbon. And then the hydrogen would have gone off of this one, all right? And it's still there, but in the zigzag form, we don't have to show that group, right? So in the zigzag form, we don't have to write it in. All right, on the last one, don't forget, anytime this is our acid catalyst, and this is our water, we're going to see an OH and a hydrogen on the 2 carbons. All right, now this one's a little bit trickier. So initially, we would want to add the OH here, but this is going to be a secondary. So we have to think, if we move this over one, can we go up in substitution? And the answer is yes, right? We can go from a secondary to a tertiary. So the alcohol is actually going to end up adding to this carbon. And what's going to happen is we're going to move that implied hydrogen, right? Is going to shift over once we make that carbocation. All right, we haven't made that carbocation yet, but once we do it, it'll move over. And the way we see that manifest in our product is we're going to draw the carbon chain exactly the same. And our OH shows up here. And that hydrogen from the water molecule ends up down here. And the one that shifted ends up here. All right, and so we're going to have that group here is going to move over. The double bond would have originally grabbed this proton and put it off the end. All right, so I hope now that we've seen a few examples, it's starting to get a little bit easier when we kind of keep working forward. All right, the next one we're going to do is halogenation. And actually, I think this is a little bit easier than what we just did. The reason I say that is there's no rearrangement with these. All right, so when you're adding Cl2 or Br2, you can put in your notes, there's no rearrangement. So this is really nice. The other thing is they're the same 2 atoms. So we actually don't have to worry about them, which one's going to add to the more substituted, which one's going to add to the least substituted, because they're the same. Right? And so what we actually see is we find our double bond, and we're going to add a bromine to each carbon that was part of that double. We still lose the double bond, but we add 1 bromine to either one. Same thing would be true if it's chlorine or bromine. Right? Last thing about this is dichloromethane and just my solvent. So it doesn't show up in my product. It's just to help things mix, right? You want to get stuff where they can interact and bump into each other. One more kind of wrinkle for this. They always add anti to each other. So they have this anti-stereoselectivity. So which means when they add across a double bond, they're going to point in the opposite direction. All right? Doesn't matter which one of these you make wedge and which one you make dash, as long as they're opposite. And actually, they tend to give you the racemic mixture because they'll give you both of them. All right, so this one was wedged, this one's dash. But when we're looking at the 2 we've added, they're always going to have the opposite stereochemistry. One will be wedged, one will be dashed. If you drew it in the plane of the paper, one would point up, one would point down. All right, so they're just going to always give the opposite face, right? They're going to add exactly opposite each other. Okay. And let me just show you why. And so this is why they always add opposite to each other, and they also don't rearrange. Right? So what happens is the double bond is going to reach out and grab one of those halogens. Right? So in this case, it's a bromine, and it bumps the other bromine off. You do form that carbocation, but the difference here with the halogen versus the hydrogen is you see how the bromine has these extra electrons? So you can actually share these electrons in and make this bromonium triangle. All right, so do you see this triangle here? And so while bromine doesn't like being in a triangle, doesn't like the positive charge, everybody has a filled octet. And the octet is the #1 rule in our Lewis dot structures. So this actually helps stabilize that carbocation. You still have that negative charge on the bromine. So on the step down here, once we've made that triangle, it's really reactive, right? Because we said that cyclopropanes have too much ring strain. So it wants to open, but you'll always attack from the backside. So it'll attack from the opposite face, and it's going to be like dominoes. It's going to hit this carbon and kick up. So we're going to push those electrons on the bromine, and that's why these two point exactly opposite each other. Right? The problem is you can attack either the carbon on the left or the carbon on the right. See how this bromine can hit in and push up? And so that's why we get two different compounds, right? And we get that racemic mixture, right? The mixture of our right hand and our left hand. Yeah. Last thing, if we draw this in the Newman projection, the whole point is that these two are opposite each other when this happens. And so you'd actually be looking right down this carbon bond from the side. And so that's why one bromine is pointing up and one's down. And the same thing here, one's pointing down, one's pointing up, right? And we get those two different products. Okay. All right, so let's try this. So if you have this compound, let's try it with chlorine. So we're going to add Cl2. So go ahead and pause the video and draw me the product of this reaction. All right, so the nice thing about the chlorination and bromination is we only care about the two carbons that were part of my double bond. So I'm going to redraw the carbon chain just the way it was. And then the two carbons that were part of the double bond, each one just gets one chlorine. We'll draw one chlorine pointing down, one pointing up. Now, the difference on a straight chain, right, where it's just kind of this linear chain, you can rotate around this bond, right, so they can flip force. When it's in a circle, right, in the ring, that's when they're locked. We draw the dashed wedge, right? But the most important thing is you're going to add a halogen to either carbon that's part of the double bond, right? And no rearrangement because we make this bromonium triangle instead of just a normal carbocation. All right, so here's a few more. So go ahead and pause the video, give these a try, and then we'll do them together. All right, let's see how everybody did. So if you're stuck, the first thing I would do is just redraw the molecule exactly how it is. So let's draw it just the way it is. We know that we're going to add to those two carbons. And on all of these reactions, we're losing the double bond. So we're going to keep the double bond off. And then we'll just put one bromine on either carbon that was part of the double bond. So I'll put a bromine here and a bromine here. We can do the same thing on the next one. We're just going to redraw our cyclohexane. Remember, we lose the double bond, so that's gone. And we're just going to add a chlorine to each one of these carbons that was part of the double bond. And we got to make them trans, right? So they're going to add to the opposite face. So the way we can show that is we can make one wedged and one dashed. And then we could also draw it to enantiomer. Right? So this would be dashed, and that'd be wedged. All right, let's try one more. Let's see how we're doing. Draw the carbon chain exactly the way it is. We know that we're going to add the bromines to each carbon that was part of the double bond. So let's go ahead and do that. We're doing bromine this time. So we get one bromine off that carbon, one bromine off the other. All right, so I think these are actually a lot easier because you don't have to worry about rearrangement. You don't worry about Markovnikov's rule. You're just going to add one halogen to either carbon that's part of the double bond. And then if it's in a ring or something like that, they're always going to add opposite each other, right? So they're always going to add opposite each other. So they're going to put in opposite directions. All right, one more wrinkle to this. Halohydrin is the same thing we're doing, but we're going to add it in the presence of another nucleophile, so like water. All right, so in this case, you're going to add an OH to one of the carbons and a halogen to the other. All right, it's regioselective, meaning there's a preference, so we're going to have to know which carbon gets the OH, which one gets the halogen. The OH is going to add to the more substituted carbon. Right? You're still going to have the anti-selectivity. So anti means trans, or they're going to point in the opposite direction. All right, so just like before, there's not going to be any rearrangement. So we're going to add one group to that carbon and one group to that carbon. Okay. So what I want you to do is pause the video and draw me the major product. All right, so think about, with those hints up above, what your product's going to look like, and then we'll do it together. All right, so let's see how you do. All right, so hopefully this went well. Let's draw our cyclopentane. Remember, we always lose the double bond. Now the question is, which of these two is the more substituted carbon? This one's attached to 1, 2, 3. This carbon on the bottom is only attached to 1, 2 things. So the one on the top is a tertiary. The one on the bottom is a secondary. So the more substituted carbon gets the OH, right? And the OH is going to come from the water. So we're going to put our OH here and our bromine here. Now, the other thing about this is it says it adds anti. So the way that we can show these two added anti is we'll make one of them wedged and one of them dashed. Now, just to kind of have this in completeness sake, right? If we're going to say these are in the plane of the paper, this one's wedged, then this methyl group stays, but it actually has to be dashed. Right? We can draw it to enantiomer, where the methyl group is wedged, and my alcohol is dashed, and my bromine is wedged. All right. How did everyone do? I think it'll get easier as we keep practicing. Let's try one more. We'll do chlorine in the presence of water. Same idea as we did above. Give it a try, and then we'll do it together. All right, so let's see how everybody did. We want to draw our carbon chain. Remember the OH, oh, sorry, and up above, I didn't write, we have to have plus HBr. Right? And that's the side product, right? So we only used one of the bromines, and we lost a hydrogen, and that's where it goes to make HBr. And we'll see the same thing here as HCl. All right, so remember the alcohol is going to add to the more substituted carbon. So in this case, it's going to be this carbon versus this one. The inside one is the more substituted, so it gets the OH. The outside one gets the chlorine. All right. And then we can write plus HCl. And I just drew the one product. We actually don't have a chiral center here, but we do have one here. So we would get both the wedge product and the dash product. All right, so here's both of those reactions. So let's go ahead and give it a try. So pause the video, try both of these, and then we'll see how you do. Or actually all three of them. Let's give it a try. So if you're stuck, the first thing to do is just redraw the molecule without the double bond. All the double bond reactions we've done so far always lose the double bond. All right. So we're going to lose that double bond. These were the two carbons that were part of my double bond. And now each one just gets a bromine. All right, so we'll put a bromine off one of them. And we'll put a bromine off the other. Okay. Same thing for the next one. Here's my two carbons that were part of the double bond. In this case, okay, it's bromine and water. So that means one of the carbons is going to get a bromine. One of them is going to get an OH. The OH goes to the more substituted carbons. This one's attached to 1, 2, 3. So this is my tertiary. This is my secondary. So the tertiary gets the OH. The bromine goes to the least substitute. All right. And then the same for this one, we get plus HBr. We don't get plus anything here because we use up all of our atoms. Same thing with the cyclohexane. Or sorry, this is cyclopentane, but it's 5 carbons. Sorry about that. We get cyclopentane. We're going to add 1 chlorine to each carbon that's part of the double bond. And remember, they're always going to add trans. So we'll get the chlorine and the chlorine. And then you can do plus its enantiomer. All right, hopefully this is starting to get a little bit easier for people where you can see all the different molecules. All right, one more review. So we've done a bunch of different reactions. So again, pause the video, try these, show me what you get, and then we'll do them together. All right, so let's see how everyone did. So when you have water and H2SO4, we're going to add an alcohol group to the more substituted, and then a hydrogen goes to that least substituted. Okay. What I would see is the hydrogen's going to add here on the end because it's more hydrogens implied here, right? They're not shown, but they're implied. So the carbocation would add to this inside one. This is attached to 2 carbon, so it's a secondary. But if you look, right next to it is a tertiary carbocation. So what we can actually do is have a hydride shift, and we're going to move that hydrogen over. So when we draw our product, we actually get the alcohol off of this carbon. You know, we lose the double bond, and this was the product of a hydride shift, right? This moved it up, which meant our carbocation went down to this tertiary, right? The tertiary is more stable, and so we get the alcohol in that bottle. We don't see the SO4 anywhere because remember, it's a catalyst, so the H2SO4 doesn't show up in our product. All right, the next one is even easier. All right, we're going to add a chlorine, 1 to each carbon. Okay. And so when we draw this, we put our 2 chlorines. And they were each where that double bond was. We lose the double bond and add a chlorine to each one. Last one, we're going to add a chlorine to one atom and an OH to the other. Remember, the OH is going to go on the more substituted of the 2 carbons. So we're going to compare the 2 that are part of the double bond. And remember, for when it's Cl2, Br2, we're not going to have rearrangement. Right? So we can redraw the molecule. And this is where, let me draw the product and then I'll tell you my thoughts. Here's where the double bond was. We want to see which one is attached to more carbons. This one's attached to 1, 2, 3. This one's only attached to 2. So my alcohol is going to come off of this carbon, my chlorine off the other, and our byproduct is HCl. So what I was starting to say was, even though these molecules might start having more going on, especially this bottom one, we've got a ring, we've got these groups branched off, your attention should go right to the double bond. And we're just going to follow that idea. The OH is going to add to the more substituted, the chlorine to the least substituted. And if you just kind of have your rules set, you can almost ignore everything else. It's just coming along for the ride. So you're just going to redraw it. So really just pay attention to that functional group, right? What's happening at that double bond? And if it's going to rearrange, okay, we might have to look 1 atom next to it, but that's it, right? So we don't want to make the problem big. We want to make it really small so we can just focus right on what actually matters. And it's typically that functional group. All right, class, I hope that